Hello, Berlin. So only for OffensiveCon I can wake up too early and deliver the talk at 7 a.m. But today we have a lot of stuff to discuss, and actually I'm very happy to be on the stage again on OffensiveCon. And I'm Alex Matrosov, Alex Ermolov is here, and Yegor Vasilenko also being a part of this research. And we will be discuss today UEFI firmware vulnerabilities, past, present, and future. Who we are, and we represent here binarily UEFI Explorer team. And actually binarily UEFI Explorer team focused on offensive research, and we continuously committing to actually apply our offensive research to defensive practices and protect the companies which we're working with. You can find a bit more on these links about our research and something else. So, but let's talk about how many vulnerabilities we will be talk today, deliver in our talk today. 1, 2, 5, 10. No, it's actually much more. And we will be talk about 28 vulnerabilities which been discovered by our team. And today is another 5 date of disclosure for HP. And let's go. Actually, these 23 vulnerabilities being disclosed earlier this week, and we specifically target this disclosure for OffensiveCon conference. And you can see here's a lot of vulnerabilities related to system management mode of x86 ecosystems, where basically you can get privilege escalation or code execution, choose memory corruption. And to be honest, finding UEFI firmware vulnerabilities, it is addictive, as you can see. And we want to thank Inside PCR, because we want to acknowledge their work, and actually they've been collaborating with us and very productively fixing the vulnerabilities we discussed with them. Also, it's another 5 we will be talking through our talk today. It's related to the HP, and also we want to acknowledge the collaboration between HP, PCR, and binarily to make these vulnerabilities fixed. All right, what these vulnerabilities stand for. And you can think about like, okay, we have this privilege escalation to system management mode, or we have code execution in system management mode, what we can do. And to be honest, usually such vulnerabilities can be used for the second stage of exploit to gain persistent into the firmware, even if, as example, you don't have a right primitive or basically spy flash or firmware storage protected. It is still a lot of possibilities for the attacker. Deliver, as example, in memory implant to the system management mode, not persistent, but as example, servers not reboots very frequently. Also, you can bypass secure boot and other integrity checking policies. Also, TPMs and health attestation for device will not help, because basically PCR's registers on TPMs doesn't extend after runtime happens, right? So basically, you have a particular state of your system when the system boots, but if you have a runtime exploitation, such of the mitigations doesn't help, unfortunately. And also, recently Kaspersky Lab discovered Moonbound, so such of the firmware bootkits and implants can be used, such of the vulnerabilities we will be talking today, to deliver payload into the firmware. But why that happens? So first of all, most of the vulnerabilities we will be talking today, it's not targeting a single vendor, it's targeting multiple vendors, because it's been found in the reference code. And basically, I think everyone knows what the log4j issue stands for from the previous December. And I would say pretty much similar problems can be happens on any ecosystem where the components get reused and adopted by multiple vendors without changes, right? So basically, if you find vulnerabilities in such component, it can be applicable for any vendor, not just one. And From this disclosure, it is actually 25 vendors, different vendors being targeted by the vulnerabilities we disclosed. Hopefully everyone from this disclosure already get fixed in their device ecosystem. Most of them did, and that's a good news, but update your firmware. So just briefly about UEFI ecosystem, right? So we have a Intel AMD reference code, we have a Tiana Core EDK2 reference code, but also we have another layer, which is called independent BIOS developers, which is actually developing another layer of the reference code, which is get adopted by many other companies. And to be honest, like device manufacturers usually not develop much code themselves. They usually develop some piece of the code, which is target specific device for some particular features, which is unique for the device itself, but not for UEFI ecosystem. And also, if you think about UEFI firmware, it is actually cool operating system inside your computer. It is over 6 million lines of code. It is actually bigger than nowadays Intel's kernel, right, from Microsoft. And of course, such of the huge attack surface can be impacted by multiple vulnerabilities. Few words about disclosure. First of all, like coordinating disclosure with multiple vendors, it's tough. And of course, like one single company can't do it very well, because first of all, if you're disclosing with one vendor, usually this vendor cares more about their security posture, and they don't basically pay much attention to disclosing or like cover everyone who potentially can be targeted by such vulnerabilities. It's why the best probably approach in such of the industry-wide disclosure to pick independent party like Carnegie Mellon CERT-CC to basically go through all the vendors with the same time and same dedication. And what we did, and actually Linux firmware volume service LVFS helps us a lot to actually scope all the targeted vendors and get them in time updated about these vulnerabilities and sync this patch cycle with everyone who is actually impacted. But the firmware supply chain condition unfortunately exists. What does that mean? Update process is actually asynchronous, have an asynchronous nature by design. And between patching vulnerabilities and upcoming fixes and third parties, it is always exists some time frame, which is actually create some sort of race condition. When, as example, reference code vendor release earlier the patch, or as example, device vendor released earlier the update, and new fixes didn't apply to this update, and the next patch cycle will be in the few months. And usually that happens, which actually creating the problems when multiple devices can stay unfixed with even known vulnerabilities. And this picture just illustrating what I've been saying on the previous slide, and exactly what's happening. It is race condition on different layers of delivery of the patch to the endpoint system. And of course, customer get hurt always in such of the process. But disclosing vulnerabilities and get them fixed, it's two different problems and should be, of course, solved separately. But let's go more about what we will deliver in this talk. We'll be talking about more vulnerabilities, mitigations, and how it will be bypassed. But also, of course, we need to provide some tooling to detect such of the vulnerabilities. You can find our firmware hunt tools in our GitHub repository. It's open source, so you can just use for the detection. All the firmware hunt detections available. All right, so let's focus on the vulnerabilities, and I will be spoiled a bit. In the next part, you will see the full SMM RLP exploit, never been presented publicly before. Alex, stage is yours.
Okay. Thank you. Hello, everyone. Thanks for coming. So we'll start with the discussion about a perfect example of a component in supply chain, which initially has a complex architecture and wasn't intended to be much secure. First vulnerability discoveries in this component made developers to apply accurate and targeted security fixes. However, the initial complexity of and insecure design of this component of this module created the opportunity to discover more variants of those bugs and even rediscover it multiple times. So that's why we call this part of the presentation as the past. So as you can see, we are talking about the USBRT component, which is the part of MEI UEFI firmware code base used by a lot of vendors and shipped to millions endpoint users. And as you can see, it has an initially complex architecture. It has DXC part, it has SMM part. All of this intended to handle USB events in boot time and in runtime. And for these purposes, there are multiple software and hardware SMI handlers in this module, and the DXC and runtime SMM part are communicating to each other through an object, a huge complex object called USB global data, and this is the point this is the starting point of attacks, because it has a lot of pointers inside it, a lot of nested pointers inside it, and even the function pointers are also stored in this huge data block, so, which is stored in untrusted for SMM, untrusted memory, system memory. So if we'll go next, we can see that the first wake-up call happened in 2016, and no, it was the previous slide. Yeah, this is the one. Yeah, the first wake-up call happened in 2016, and we go briefly through this vulnerability. As you can see, untrusted input for software SMI handler of USBRT. It extracts from extended bias data area the pointer to a struct. We call it a struct pointer. The pointer is passed through with no sanity checks to a function, and this function writes fixed data byte F0 to the data pointed by this by this pointer structure pointer. And as you can see, untrusted input, no sanitation, and memory corruption, classical memory corruption vulnerability. So let's go next. So a few years ago, in 2017, another vulnerability was discovered. It was discovered also in Intel NUCs, and let's go next. The vulnerability itself was a bit deeper than the original one. It was a call out, and the vulnerability. So I'm showing it on the exact code page, so you can understand what I'm talking about. Again, untrusted input, software structure pointer. It was sanitated later. We are not talking about sanitation the structure pointer. However, there is a call. There is an index which is extracted from a structure pointer. This is the function index, and the function is called from a USB API table. And this table contains multiple functions which could be called, and attacker, a caller of this software SMI handler can specify which function will be called. So in the next slide, you can see that here is this table on the left, and the function USB API function number 14 in this table leads to a call out. It leads to a call that where a function and parameters is extracted from structure pointer, and from the structure pointed by structure pointer, and there is a function block which allows to call an arbitrary function, an arbitrary code, and specify up to 7 parameters in it. So yeah, they try to patch it with adding the validation for structure pointed for USB global data. So they actually, the first attempt was like adding the sanitation of pointers, of course, and then validation of the protecting the pointers that are actually should point to SMM, like function pointers. They started to protect this block with CRC32 checksum, which is actually not strong enough to secure the data, and there is a method to spoof it. There's a project that can allow to do it automatically. So let's go next. Here on the left side, you can see the CRC table initialization routine, which was initially applied with a static polynomial, and to fix in the second try to fix this vulnerability, they applied a dynamic polynomial, which was extracted, as you can see in the center, from the MEI USB SMM protocol, which in turn it extracts it from power management timer. And this value, though it will be unique for different systems, of course, but for exact system, exact firmware, exact hardware configuration from boot to boot, in most cases it won't be different, but for like brute forcing, they have added the log flag that allows us to make only one attempt per boot to use this software as my handler, and this solution, well, it kind of worked. Let's go next. It kind of worked, yes, but no. There was another discovery of the vulnerability in USB-RT, but not in Intel Unix, in Intel servers. It was in 2020. So you can go next, please. Yeah. So in 2020, exactly the same vulnerability was found that was in 2017. USB API function number 14. No CRC32 validation wasn't applied at that moment, and this is a classical example of where fixes delivery problem exists for different product lines, even in one vendor. So inside, as you can see inside Intel devices, hierarchy code branches could be kept not up to date in years. And however, this was not enough. And on the next slide, this was not enough for us. And as we can see in 2020, again, one another time in Intel servers, the vulnerability were discovered in another function from this USB API table, and this function allows to call out from SMM all pointers for all the data for calculating the function pointer in the highlighted block are extracted from the USB data, which is in system memory. Hence, it is controllable by an attacker. And at this point, CRC32 with custom table was applied, but it was not covering all USB data contents, and that was the vulnerability. So there was another discovery under the same CVE. The vulnerability, it is the same, exactly the same callout, exactly the same, quite similar formula to calculate the function pointer, which is extracted from the untrusted input global USB data. And but the difference is that all previous vulnerabilities were in software SMI handler, but this one is in hardware SMI handler. Well, it may be quite more tricky to trigger, but it handles USB events. Finally, in 2021, we can see a rollback to 2016, where original vulnerability was found, because in 2021 in ASUS devices, exactly the same vulnerability that were found in 2016 were found and reported to vendor. So as you can see, 6 years vulnerability lives without any fixes, and it actually lives longer, as we will see a bit later. So let's go next. So what is happening in present? In present, we recently saw some big news from us. We have discovered pretty long list of vulnerabilities, even for UEFI, but they similar to problems that were presented in a few years past, and we can see that in some cases industry doesn't learn. So the first type of the vulnerability is the call out in the software SMI handler. We cannot talk much about details because we have no time for it. All the details you can find on our GitHub and on our website. So I'll just go from one type to another and just describe it quickly. So the first type is the call out from the EFI runtime services, which is stored in system memory. Hence, a call out is possible. This is the code from software, from some software SMI handler. And we found just one such vulnerability. Now, on the next slide, we can see that there. No, this is go to the previous, please. Previous. Boot services, yes. Boot services. We can, as we can see, there are more than one vulnerabilities in this type call out through UEFI boot services, which also is stored in system memory, which is untrusted for SMM. And on the next slide, there are a bunch of memory corruptions. Oh no, this is the call out, the non-SMM protocol, which is located by the boot services in the boot time, and for an SMI handler uses it as like this without any sanitation, and as a system memory object, which allows an attacker to hijack the execution flow, like in previous cases. And on the next slide, more than one, again, memory corruption vulnerabilities, most of them through communication buffer, which is also untrusted input for child software SMI handlers. Status codes, fixed bytes, keywords, div words, and other data is written through two pointers nested inside the communication buffer. So it is not a tricky thing to exploit those issues. And we have also another, just one stack buffer flow vulnerability, which can be executed during boot. And this is a classical insecure handling of EFI variables. Alex will talk just a bit more about that regarding some HP vulnerabilities he promised. So we have disclosed. We have reported them, of course, to Insight, to the vendors, and as you can see, a lot of vendors affected, more than 25, if I remember correctly, millions of devices. But the industry examples, live examples, show us that in many cases the asynchronous nature of the supply chain and updates delivery in firmware industry show us that probably and most likely a lot of those vulnerabilities will be unpatched for a long time on endpoint devices, and they can be stayed like that in years, as we saw just before. And so this is the time to ask our dear friend USBRT, how is it going with this module in 2022? And in 2022 we saw a device which has which receives updates in 2021, which was still receiving updates in the past year, and it has for 4 years the vulnerability 20, which was discovered in 2017. It was existing, and it was existing as a 0 day on this device, and it's still exploitable. And the most popular mitigation, like SMM code check enabled, which doesn't allow to execute code outside of SMRAM. This is a mitigation from callouts. It was not enabled on this system. So let's go to the description of this vulnerability. I just remember that there was a call of an attacker can call specify a call to invoke the USB API function number 14, where all parameters are controllable by an attacker and extracted in the global USB data. And an attacker can even specify arguments from 0 to 7 arguments to invoke any code. And the proof of concept for this vulnerability actually was released 4 years ago, and it was working for us just like that. We just made some fixes to make something useful. We on the next slide we can demonstrate it works on this system. This is Kaby Lake, still receiving an updates, but with 0 days inside. And as you can see, there was a dump and a starting of the SMRAM dump in the beginning, which is the signature SMM S3 underline 64. This is the content with which most likely in the beginning of SMRAM is stored. So the future. In the future, we have the next slide. Yeah, thank you. In the future, we have again USBRT with 2020 version of the vulnerability discovered in the wild, receiving updates, and at this time the mitigation was set, and this made us try to bypass this mitigation and and apply the ROP technique, which is known for years, but for UEFI it wasn't, at least in public, it wasn't presented before. So let's see how it goes. So just a few details about the vulnerability to remind you. There was the USB API function number 2 in the table. We can, as an attacker, can call it. So CRC 32 is bypassable. There was no patch at this time for against spoofing CRC, just like that. And the vulnerability leads to call an arbitrary function, but in this time we cannot control the parameters, and that's why we have to build the code that creates such parameters using our ROP technique. So Let's go to the next slide. There is a perfect examples to build ROP techniques in UEFI firmware because these two blocks, set jump and internal long jump, you can find these gadgets in almost in any TXC and SMM driver, and that allows us to build a stable rope chain just for one driver and using the code only in this driver, and we don't need anything outside of this driver and outside it code pages. So the first yes, the first gadget is used to leak register values, including RSP. It is very important to leak RSP because we will make in future some calls and we will have to restore it to not crash anything. And to leak it, we have to, the leakage is performed to the address which is very relevant to what's stored in RCX. In our case, RCX stored a pointer to a memory to a system memory, some area in system memory, and in this case we doesn't have to do anything with that. But in case you will face the situation where RCX is pointing to an SMRAM and you cannot access the SMRAM to read those leaked registers, you will have to use another gadget, internal long jump, which will perform a move instruction of 0xE8, which this address is available on almost any system. I suggest it will change the ECX register, means RCX, and that's how you will change it, and then you are free to call. So about RSP, there is a pop RDX. There was a pop RDX instruction in the gadget we used, and this will allow us to restore the stack and continue execution without crashing anything. So at the step one, we know how to read the register and we know how to write the register using those different gadgets inside set jump and long jump and internal long jump function. And we need something useful. We would like to try to read SMRAM again, once again, this demonstration, and that's why we decided to use the copyman function, but we have to specify its parameters, its size, source, destination, and size, which is R6, RDX, and R8. And that's why we have to find the gadgets in this driver. We found it using Gropper tool, and this is just specifying R8 and RDX and R6 registers, and these gadgets are widely used in firmware, in TXC, in SMM, because these code patterns are used to work with UEFI protocols, and this code is pretty spread for those type of drivers. And so this at the step one, we are specifying in the first line of code, we are specifying R8. Then we specifying the address of the gadget that will create R8 value for us correctly. And then we specify RDX and RCX in the next gadget, and in the next gadget we are performing internal long jump to restore all values of the registers and set RSP to because we made some calls, and that's why we have to restore RSP to its previous condition for not crashing anything. And then we are performing the third gadget will perform as the jump instruction to copy mem, and it will go smoothly. Next, please, slide. So this step two exploitation. This is a part of the proof of concept for it. I think we are going to publish it So we are specifying the data in the controlled memory, controlled by and pointed by which will be pointed by RCX. Then we are specifying the USB data, USB global data to actually exploit the vulnerability to trigger it, and then we are triggering the software SMI handler, and as a result, we with our copy memory routine are extracting 1 byte from SMRAM. And demonstration. Let's see how it goes, roping the SMM. So as you can see in this demonstration, the first lines are the register values extracted using those gadgets, and the second is the SMRAM dump. And as you can see, again, the signature SMM-S3_64 is at the beginning. That proves us that it is an SMRAM contents. The mic is yours, Alex. Thank you.
Yeah, so actually, Alex, thanks a lot. I think that's been pretty interesting demonstration about ROP exploit into SMM. And I would say on public, it's been not available any sort of examples about how we can actually create a full chain of ROP exploit to into SMM. And bad news for mitigation developers, it's actually bypasses SMM check completely. And to be honest, it is very hard to mitigate such of the problem. But I think a bit later on the slides, we will cover some new topics about the mitigations. And of course, it is a lot of things moving forward in terms of defense. But let's focus on some other vulnerabilities we want to discuss today. And in our presentation with Alex Terushkin and Adam Zabrowski on Black Hat US in Vegas last year, we've been talking a lot about also misuse of the get variables and actually how common it is, and still very broadly available in x86 ecosystem, especially on servers, which is pretty scary. So let's actually talk through how these vulnerabilities, memory corruption vulnerabilities can be exploited. And so first of all, we developed the tool called UEFI Explorer. It's an IDA Pro plugin, which helps to reconstruct UEFI specific semantics and types, and actually much simplify a lot the reverse engineer life for actually digging into UEFI firmwares. But also we developed some generic checks for such of the problems like a misuse of the get variables. Unfortunately, we mentioned this multiple times. We share these thoughts with the developers, but I think they still not use it, such of the plugin for basically detecting the problems in their firmwares. Of course, it's a simple heuristic. It can create a lot of false positives, but basically, visually, you can recognize if it is a real issue or not. Let's look on the left side of the pseudocode window. Basically, it is exactly the classical problem where we have an initialized size once to usage of get variables when the size get reused and actually lead to a classical memory corruption problem on the stack. And also, actually, why that happens, right? So because the primary display value, it is an NVRAM value, so controlled by the attacker. And in such cases, we also can rewrite return address easily. So basically, we use QEMU to navigate this driver. And it's another bad news for the firmware developers, because you not always need actually target system available to develop some POC for that. Because in many cases, if you have the driver, which doesn't have any hardware-specific features inside, you can just emulate with QEMU. Some things you can stub it and actually lead to a particular functionality to execute the code which you wanted to test it. So basically, I would say in many cases, you can move from only static analysis to something hybrid approach where you can use pieces of dynamic analysis and static analysis together. And actually, it's very powerful. Let's look how actually exploit looks like. To be honest, it's just a classical Stack Overflow, no mitigations. It's actually very straightforward, right? So we have shellcode and just actually popping these shells inside the Dixie driver. And thing is, this system broadly spread into the data centers. This is pretty scary vulnerability. I would say it is unprivileged driver. It's not a SMM driver, right? It is a Dixie driver, but such of the Dixie driver can lead full compromise of actually secure boot, because basically you are having the driver which is vulnerable. You can have the similar effect like a boot hole vulnerability, basically bypassing boot of chain trust when you executing the code inside the Dixie phase, right? Extra code, which will be actual shell code. Yeah, so it is a demonstration in QEMU, right? But also we have another one on HP system, and it's exactly connects to our disclosure today. And let's look on this one. Same problem, right? So data size only once initialized. We have actually some sort of sanitization, but it is not creating a problem to pass it. And also data size didn't change after the first get variable call, and it leads to classical Stack Overflow memory corruption. So again, detected by UEFI Explorer. So developers use UEFI Explorer. And here, just this simple demonstration, same thing. We run in the driver, then exposing some variable, which is actually will be corrupt the memory after. So yeah, greetings from UEFI Explorer team. Looks cool. All right, but what's the next? How actually this will be moving to some of the more in-depth mitigation, right? So we're talking a lot about the attack surface reduction. We're talking a lot about many things, but complexity of UEFI ecosystem and complexity of the firmware itself tell us a lot. So that's actually such of the problems will be not changed. The vulnerabilities we discussed on this presentation today with you guys, it's not a new problem. These classes of vulnerabilities known for years. And also, I would say why it's still happening. In many cases, it's not enough knowledge base to actually learn how this problems looks like, right? How many you have exploits available, like a POC exploits available on the public? 2, 3, 5? But basically, it's not enough to learn, right? So if you look how many exploits you need to actually test your mitigations on the browser, so much more, right? So you need the fuzzers and a lot of other things, but how you can develop the good fuzzer if your development team, if you not understand how the attackers will be used, such of the practices to attack the systems, right? So basically, it's one of the reasons why we actually always try to release very detailed advisories, because first of all, we want to make a commitment to such of the knowledge base, to transfer this knowledge to the development teams and product teams to learn from such of the mistakes, because it's enough. How many years we need to repeat the similar problems? 10, 20 or more? I think we need to move something else. And also a lot of things happening in actually reference code, right? So, and this slide's talking about some sort of like a complexity of SMM itself, right? So, and in many cases, like the attacker can corrupt something and then expose the problem. And it's exactly about the SMM ready to log. So, but actually, a lot of new mitigations with fancy words like STM, PPAM, SMM-CET, Intel Hardware Shield came up recently, right? And it sounds like it's game over, right? So basically everything is mitigated, protected, done. But party is not over because its complexity of the ecosystem itself leads to many problems, and we will talk about that. So first of all, like what is Intel PPAM stand for? It is some sort of like a memory isolation based on virtualization technologies called STM to isolate each SMM driver to separate execution domain. And it's, of course, creates some sort of complexity for development, because this should be done by development team, right? And also, it is a lot of policies need to be applied, right? So, and basically we have like a first generation of STM when it's been just SMM under the hypervisor. Now it's transferred to different phase when we have actually multiple layers of memory isolation. Like now we have a rings into SMM, right? So it is ring 3 and ring 0. How it will be different from exploitation standpoint? So basically, yes, of course it will be create complexity, raising the bar, but the question is how broadly it will be adopted. And to be honest, at scale, we don't see much systems actually adopt such of the mitigations. And I really believe because it's also create few side effects. So it can affect the performance, and actually performance, it's not a friend of security, because think about most of the device developers, they care how fast your screen will blink after you open the lid on the laptop, because it's visible for users, and they will be going by another vendor because it boots faster, right? So basically, I'm not a true believer these mitigations will be available for each SMM driver. It can be for some most critical ones or not, but if you even not isolate all of them, that's already a big hole in this mitigation. Another thing, it is complexity of such of the feature itself, right? So we have actual policies apply for each driver, how it will be loaded, what kind of boundaries into the memory will be created. And of course, it can lead some memory corruption bugs, right? So because too many things can go wrong, right? And if you read something from flash storage where policies exist, it's basically can be controlled by the attacker, right? So yeah, it's some spoiler, so research ongoing, stay tuned. Oh, too fast. And of course, complexity of ecosystem and a lot of other things plays against of security. And as we can see, even this thing like a USB RT, it's not actually that complex, but it's still vulnerable and still exposing the bugs to the ecosystem. And problem is, of course, like different generation of platforms, different generation of CPUs and firmware frameworks and other things, and this create hell complexity problem. And I would say it's hard to fix it because different lines, even from the same vendor, have a different update cycles and also priorities, right? So let's say first year probably they care about, the second year less care about that, and third year they almost forget and they deliver only the critical updates. A lot of vendors do that. And unfortunately that happens. I would say most of the enterprise vendors is actually doing better than just 2 year support cycles, but still a lot of vendors just shifting their priorities for such of the platform. And we really need to just clean up the ecosystem from such of the legacy bugs and actually create more effective mitigations. That's what the industry needs, and it's exactly what this research talking about. How many years we will be exposing call-out vulnerabilities? It's been in early 2000s, it's been happening right now. We need to move on. And it's been our talk exactly about such of the topics, and we want to help the industry to get fixed. Thank you very much, and happy to answer your questions.
Yeah, thank you.